Okay, on example 3, it says a rectangular page is to contain 24 square inches of print. The margins at the top and bottom of the page are to be 1.5 inches, and the margins on the left and right are to be 1 inch. What should the dimensions of the page be so that the least amount of paper is used? So first let's see what's given. It says the page has 24 square inches of print, so that's one of our hints. It also tells us the margins at the top and bottom are 1.5 inches, and the margins on the left and right are 1 inch. It says, what should the dimensions of the page be to use the least amount of paper? Okay, so let's draw the picture. If we draw our picture, we put a piece of paper and we include our margins here. They called this side X. Top and bottom would be 1.5 inches. So this ends up being X plus 3 on this side. Over here, they called this one Y. Left and right margins are 1 inch, so this ends up being Y plus 2. Now, we want the least amount of paper. That means we are minimizing the area. So, minimal area, that's going to be our primary equation. Now, the area of a rectangle is length times width. That's how they got X plus 3 times Y plus 2. This would be your primary equation when you include the margins. Now, our secondary equation was the hint they gave us, the square inches of the print. Now, this would be equation 2. Now, the print area, just the black area, it's a rectangle again, so that's going to be X times Y. Now, remember, you take your secondary equation and you solve it for a variable. So we're going to solve this one for Y. We want to get the primary equation in terms of one variable. We don't want an X and a Y. So we're going to solve the secondary for Y so that we can substitute. If you divide by X, you get Y equals 24 over X. So this is our secondary equation solved for Y. What we're going to do is we're going to take 24 over X and we're going to plug it in right here for Y. Which is what they've done right here in red. We're going to FOIL that. So let's come over here and FOIL that. X times 24 over X gives us A equals 24. Okay, and then X times 2 gives us a positive 2X. Then 3 times 24 over X gives us a positive 72 over X. And 3 times 2 gives us a positive 6. When you combine your terms, this is what you end up with. 30 plus 2X plus 72 over X. Now we need to find the derivative of that in terms of X. Okay, so remember this is our area. So when we take the derivative of the area with respect to X, we get dA over dx equals, derivative of 30 is 0, derivative of 2X is 2, plus, now remember when we take the derivative of this, this would be written as 72x to the negative 1. Derivative of that would be negative 72x to the negative 2, which they wrote this way. So you have negative 72 over x squared. Here's our derivative. Now we're going to take that and set it equal to 0. Let's do that over here. So we're going to have 2 minus 72 over x squared equal to 0. So when we move our 2 over, we get a negative 72 over x squared equals negative 2. Okay, we can multiply both sides by negative x squared. That gets rid of that negative. Then we're going to have 72 equals 2x squared. And you divide by 2, and you get 36 equals x squared. Now, when we take the square root, that is going to give us plus or minus 6. But remember, we got to talk about feasible domain. We can't have a negative because we're talking about area. So we are only going to use the positive 6. So if you come over here, see where they have x squared equals 36, x equals plus or minus 6. And we are only using the positive because we can't have a negative area. Now, to solve for y, they took the 6 and they plugged it back in right here. So y is equal to 24 over 6, which is 4. So what that gives me is my x and my y. I know my x is 6. And let me use a different color since I've already used that one. So I know that my x is a positive 6, and I know that my y is a positive 4. So the dimensions of this side would be 6 plus 3, which is 9. And the dimensions of this side would be y plus 2, which is 6. So our paper would actually be 9 by 6 to get the least amount of paper used, which would minimize the area.